Yeah, this is Dr. J. Mohan from EC Department of Institute of Aeronautical Engineering. Today we are going to discuss about the Fourier transform section 5 in the subject of signals and stochastic processing. Last section we studied for the property of Fourier transform, linear property of Fourier transform, that is the first property. The linear property in the sense it's going to satisfy for the superposition principle as well as of homogeneity, then it's represented as a linear property. It's going to satisfy for both the condition in the Fourier transform, then it's satisfied for the linear property of Fourier transform. Next, we go for the frequency shifting property of Fourier transform. If you shift the frequency in the input side, it's going to multiply with the exponential value of how much time you are going to shifting. That means, for example, if we take for the x of t minus of t0, if we take for the Fourier transform, I represent as f of t, that is equal to e power of minus of j omega t0 into x of omega. So, how much time you are going to shift, that much multiplication, exponential multiplication is going to happen in the Fourier transform. Next property we studied for the time reversal property of Fourier transform. If you change the time in the input side, for example, x of t we take, if we represent for the minus t, then Fourier transform also take for the Fourier transform of the signal, then it's it for the x of minus of omega. So the time it's getting to shift in the input side, the output side also, the frequency spectrum also going to shift for the minus. This three property we studied for the last session. Then this session we should go for the conjugate property of Fourier transform, time scaling property of Fourier transform, time shifting property of Fourier transform, time differentiation property of Fourier transform, time integral property of Fourier transform, autocorrelation property of Fourier transform. This 6 property we should go for this section. Then first condition, conjugate property of Fourier transform. So the conjugate property of Fourier transform state that the conjugate function of x of t in time domain result in conjugate of its Fourier transform in the frequency domain, and omega represented by minus of omega. So this is the statement of conjugate property of Fourier transform. If the Fourier transform we take for the x of t, that is represent for the Fourier transform of x of t in the time domain, it's getting for the frequency domain of x of omega. So this term I should write for the Fourier transform condition of the equation. X of t, Fourier transform of x of omega, x of t, Fourier transform is represented as x of omega. If you take for the inverse Fourier transform, again we get for the x of t. That's why I should use for the both the direction of arrow mark. As per the conjugate property of Fourier transform statement, we should take for the input side as a conjugate property of x of t. That means the input side, what we are going to given for the, this is a Fourier transform system function. Fourier transform system function. If we give for the input x of t as a time domain, we get for the frequency domain of output, that is x of omega. Now you take for the conjugate of your input side, but output side also we get the conjugate, but sign value is getting to changed. So what the sign value of frequency domain changed? Minus of omega. This term I should write for here as a x of star of t, the Fourier transform we take it's produce the output as x of minus of omega star. So this term I should write like this form. So x star of t, take Fourier transform, we get for the capital letter x star of minus of omega. If we take inverse Fourier transform for x star of omega, x star of minus omega, we should get for the this x star of t. That's why I am using for the both side of arrow mark. Okay. So this is called for the conjugate property in the mathematical representation. Next, we go for the proof. We need to prove for the conjugate property as a Fourier transform condition. As the Fourier transform definition, x of omega is equal to integration of minus infinity plus infinity x of t e power minus j omega t dt. This is a Fourier transform equation when we are going to give for the input as a x of t. So this is the input. If we take for the Fourier transform of x of t as Fourier transform, we got for the x of omega. This x of omega I should write for the mathematical model of integration form. So this is the definition of Fourier transform of input. Now we take for the conjugate on both the side in this equation, Fourier transform equation. So now what I am doing, simply I take for the conjugate of both the direction. This means, so see here what we represent, that is here I should write x of, that is capital letter x of omega, capital letter x of capital letter x of omega, I should take for the conjugate for here. Then this will be, I should write as a minus infinity plus infinity x of t e power of minus j omega t dt. I put for whole conjugate. If conjugate, then I should write for the next term as this term x star of omega, x star of omega. So it will be going to dominate only the input side, equal to then integration of minus infinity plus infinity. I rewrite for this equation. This star, it will be came for the inside for here. If it came for the inside, this is got for the x star of t. Okay, that is input x star of t. Then e power minus j omega t is there. This e power minus j omega t, take conjugate, that means e power minus j omega t conjugate is represented as a e power of j omega t. That means this minus. So j minus of j conjugate is equal to plus of j. So I should write as a like this form. So now what will be happen if we take the conjugate of input side for the Fourier transform? So that will be going to converted as a integration of minus into plus into x star of t. This conjugate input side. If we take for this conjugate of e power j minus omega t, that will be converted for the e power j omega t dt as a conjugate property condition. Now we can replace the omega into minus of omega. That's it. So where the omega is present for this both the equation, where the omega is present, we should replace for the omega equal to minus of omega, because we need to convert for the again Fourier transform condition. Now I substituted for the omega is equal to minus omega for here also and here also. Okay. So what will be happen now? As per the statement of Fourier transform, what is there in the x term, that will be represented as a Fourier transform of our cases in the input side. So that's why what I am writing, the Fourier transform of x of omega is equal to, I should write minus infinity to plus into x of t e power of minus j omega t. Now here you see, here is minus omega t. At the same time, here what it is there, it's represented as a x star of t. That's why this term, that is this term, it will be write as what is there here, that will be represented as a Fourier transform of t. I should write for the x star of t. Now if we take for the complex conjugate of Fourier transform, then we get for the output is x star of minus of omega. So see here, Fourier transform of x star of t is equal to x star of minus of omega. We write for the equation. Otherwise, we should write for the general condition of complex conjugate Fourier transform as like this one. So x star of t, the arrow mark of both sides, Fourier transform, capital letter x star of minus of omega we should write. So then, if we take for the inverse Fourier transform of x star of minus omega, automatically we get for the x star of t. This is represented as a complex conjugate property of Fourier transform. Next, we go for the another property is represented as a time scaling property of Fourier transform. The time scaling property of Fourier transform state that if a signal is expected in the time by a quantity of A, the signal is expected in time by a quantity of A, then if Fourier transform is compressed in the frequency by the same amount, how much we are going to multiply with the time scaling case in the input side, that much frequency components are compressed in the output side of condition. That is called for the time scaling property of Fourier transform. Now, I should write the Fourier transform system. This is Fourier transform system. Then we give for the input is x of t. We get for the output is x of omega. This is the case. So what is that? How much time is there? That much frequency is going to happen. Now, I multiply with the time of some constant, that is quantity of t, x of t a. Okay. So this is a is represented as a positive integer. A is represented as a positive integer. At the same time, a is called for the constant. Now, how much you are going to multiply the output? This is a Fourier transform system. So, it's produce the output. It's represent for the 1 by a of x of omega divided by a. So, this is represent for the 1 by a in the sense it's represented as a compression values of frequency. So, this is called for the time scaling property. As a statement of Fourier transform, we take for the Fourier transform of x of t is equal to x of omega, capital letter x of omega. Then we take for the inverse Fourier transform of capital letter x of omega, we get for the x of t. We used for the arrow mark on both the sides. Now, as per the statement of time scaling property, we should multiply with some constant in the time domain of input side, that is x of a of t. Take the Fourier transform is equal to 1 by mod of a x of omega by a. This means what is it? That means the frequency is going to compress for the how many time we are going to multiply with the constant the time domain of input, that much is going to compress in the output side of frequency. So this is represented as a time scaling property. Now we take for the a value is greater than a, then a value is represented as a greater than of 1, then xa of t is a compressed version of x of t. That means frequency of output side is getting compressed. When a lesser than of 1, then the function x of t is represent for the expand the version of x of t in the output side of Fourier transform. So this two function is going to arise when we are doing for the time scaling property. Suppose if we can compress for the output side of frequency, or if we can expand for the output side of frequency, both it will be going to happen. Okay. So now we need to prove for the time scaling property of Fourier transform. Now to take for the definition of Fourier transform, the Fourier transform of x of t is equal to x of omega. We write for the mathematical term as integration of minus into plus into. The input is x of t e power minus j omega t dt. Next condition, we should apply for the t is equal to at, because of we need to multiply with some constant. So that's why I write where the t is present, I should apply for the t equal to a of t only when the input side. Okay, so the Fourier transform of here t is there, that's why I should apply for the x of at. Fourier transform of x of at is equal to integration of minus into plus into, instead of this t I should apply for the x of at e power minus j omega t dt I wrote. So next condition, now I should write for the u is equal to at. Okay, I need to substitute for the e equal to at. Then what about the t? T is represented as here u by a, I changed. Then dt is equal to du by a, we can write. Now this all value we need to substitute for the previous case of equation. So that is f of x of at is equal to integration of minus b plus into. Here is how the at is there, that's why I apply for the u e power minus j omega. Here is how the t, the instead of t I should apply for this value, then dt is there, that due to that condition I apply for the du by a. Now we take it out for the constant as the statement of f of x of at. So that means 1 by a, here is du by a is there, you take it out for the integration, because of that is not related with the u term, we take it out 1 by a, integration of minus into plus into x of u e power minus j omega by a u du, we write. Now this case it will be going to have the two condition. The case 1 is represented as a greater than 0 and the case 2 is represented for the a lesser than 0. Then how to represent for both the condition? F of a of t is equal to 1 by a integration of minus into plus into x of u e power minus j the omega divided by a u du. That I should write for the 1 by a x of omega by a, I should write here. We know the Fourier transform, that is Fourier transform of x of t, we write as x of omega. So that value is integration of minus into plus into x of t e power of minus j omega t dt we wrote. So what the omega here, omega is there, that's why I should write for the x of omega. So in this omega place, in this equation what is there here? W divided by a. So due to that condition, I should write for the x of w by a for time scaling property condition. For the first condition of a is greater than 0. Suppose a is lesser than 0, it's represent for the minus values. So that means minus a, that is minus 1, minus 2, minus 3, something is going to happen, that will be represented as minus. So that condition, what the time scaling property is doing, f of x of at, the a is minus values. That means we take it, we represent but that minus value into the outside. Okay, so integration of minus into plus into, that is 1 by a, we added for the minus here, x of u e power minus j e omega divided by u du we write. So now here is going to have minus, that's why I should write for this value as minus of 1 by a x of omega by a, I should write. Okay, now I should combine for the both a is greater than 0, a is less than 0. When you are going to scale for the time in the Fourier transform, we don't know whether that is represented as a is greater than 0 or whether a is less than 0. So generally I should write for the term as Fourier transform of x of at is equal to 1 by mod of a x of omega divided by a. So this 1 by mod of a is represented as a, whatever maybe if we are going to get for the negative value, automatically it's going to convert it for the positive value in the outside. So generally we can write for the Fourier transform of time scaling condition, x of at is equal to Fourier transform 1 by mod of a x of omega by we write. So this is represent as both the condition is getting to satisfied for the our time scaling property. Okay. Next condition, time shifting property of Fourier transform. So the time shifting property of Fourier transform is state that if a signal x of t is shifted by t0 in time domain, then the frequency spectrum is modified by a linear phase shift of slope of minus of omega t0. How many time shifting is going to happen? That much linear phase shift of slope is going to happen for the Fourier transform condition. So that case I should take for the minus of omega t0 we take. Okay. As a definition of Fourier transform, x of t Fourier transform is represented as a capital letter x of omega. Now this based on this condition we take for the time shifting. Okay, we take for the input x of t we taken, then Fourier transform we should write, then we write for the x of omega. Now this x of t is going to shifted for the some t0 time. Insist of t is going to shifted for the t0 time. So that means what is the Fourier transform is going to happen? So the exponential value of j omega 0 t into x of omega. So how much time is going to shift? Minus of omega minus t0 times shift. That's why it's going to multiply with e power minus j omega 0 t and x of omega. This x of omega in terms of x of t. So this is represented as a statement of time shifting property of Fourier transform. That means if you are going to shift for the time domain, the spectrum is modified for the linear phase shift slope of minus of omega t0. If we shift for the t0 time in the input side, the spectrum frequency spectrum side linear phase shift is going to happen for the slope of minus omega t0. Okay, then we go for the proof of time shifting property of Fourier transform. As Fourier transform, take for the x of t in the input side, it's produce the output is capital letter x of omega. Here, insist of t, I should substitute for the input side as t minus of t0. Take for the Fourier transform, it's multiply with the e power minus j omega t0 into x of omega. This is we call for the frequency spectrum is modified by the linear phase shift slope of minus of omega 0. That is called for the e power minus j omega 0 t0. Now, we should prove based on the Fourier transform condition, Fourier transform of x of t is equal to x of omega. That formula is equal to integration of minus into plus into x of t e power minus j omega t dt we write. Insist of t we can apply for the t minus of t0 in the time shifting property condition. So that will be t minus of t0, the t is equal to t minus 0. I substitute here f of x of t minus of t0 is equal to integration of minus into plus into x of t minus of t0 e power j omega t dt I write. Okay, here only I can change. Now I should take for the t minus of t0 equal to u. Then t is equal to u plus of t0 and this differentiation, that is d by dt is equal to d by dt is equal to du. Now this values to substitute for this equation. Okay, what are the values? T minus t0 equal to u, t is equal to u plus of t0, dt equal to du on this equation. After substituting, what will be going to happen for the right side of the equation? Integration of minus into plus into x of u e power of minus j omega. Here is t is there, that's why u plus t0, dt is there here, that's why we can apply for the du. Okay, now we need to simplify for this equation. So this term we can separate. What are the terms? The e power of minus j omega u into e power of minus j omega t. Two terms. Because of it's going to adding for the u plus of t0. So this you can compare to this all case. This term only is going to have t, remaining and all are the u. So that's why you take it out for here. That's the condition. The right side of the equation e power minus j omega t0 I take it out. Remaining integration of minus infinity plus infinity x of u e power minus j omega m du you get right. So you can compare with the Fourier transform equation for this condition. What you are doing? The Fourier transform of x of t is equal to integration of minus into plus into x of t e power of minus j omega t dt. So see, all the terms are t, that's why we write as a x of omega. See, for here all terms are u, that's why I write as a x of omega. Now the finally what the conclusion is going to happen for the time shifting property of Fourier transform, x of t minus of t0 we represent for the e power minus j omega t0 x of omega if we take for the Fourier transform. Now suppose if we have for the, here is delayed version. Now I add for the plus t, that is x of t plus t0, we add for the plus here. Then what is the output of Fourier transform? The output is represented as x of e power j omega 0 t x of omega only. So here is have the minus, that's why in this term e power minus j omega t0 we got. Here is have the plus t in the Fourier transform, we got for the e power j omega 0 t x of omega. So this case the slope will be going to multiply, that is slope will be going to multiply with the exponential order of j omega t0 condition when you are going to happen for the t0 time shifting in the input side. So that's why simply we can write as a magnitude spectrum as well as space spectrum, because of we are not going to make to realize for the frequency time different time shifting property of Fourier transform in the frequency domain is going to multiplied in the slope case. So that's why we go for the magnitude as well as space spectrum. We need to identify where the exact position is going to happen for the our spectrum case. The magnitude value of the signal is represented as a mod of e power j omega 0 to t0 x of omega. That e power j omega 0 t0 is represented as a oscillation together. That's why we take for the mod of x of omega only. Next condition, if we take for the phase, what will be going to happen? The phase response is represented for the angle of e power j omega 0 t x of omega is represented as e power j omega 0 t plus angle of x of omega. So if angle of e power j omega is depends upon the minus of omega 0 t only, that's why I simply write for the angle of minus omega t0 plus angle of omega 0. This means what is it going to happen for here? It is clear that the shifting of the function by t0 in the time domain result in multiplying its Fourier transform by e power minus j omega t0. Hence, there is no change in the magnitude spectrum, but space spectrum is linearly shifting. How much linearly shifting? This much linearly shifting. That is angle of minus omega 0 t0. Next case, based on the time shifting property, I should take further some example. Okay. So time shifting property of Fourier transform. Find the Fourier transform of the signal, given signal e power minus a mod of t minus 2. Okay. So this mod of t minus 2 in the sense it's maybe t minus 2 or minus of t plus 2 also is going to have possibility is going to happen. As per the statement of Fourier transform of two-side exponential signal, we studied for the last session. That will be, I take for the Fourier transform of e power minus mod of t is equal to 2 by a square plus omega square. Okay. So you take for the Fourier transform of e power minus a mod of t is represented as 2a divided by a square plus 2 omega square. So this is studied for the two-side exponential signal condition of Fourier transform. Here we got the input is minus of a mod of t minus 2 we got. So that's why we choose for this two-side exponential signal definition. By using the time shifting property, x of t minus of t0 is equal to Fourier transform is represented as e power minus j omega t0 x of omega. For here T0 you are going to shifting, that is minus of T0. Here what will be happen? Minus of 2 they are going to shifting in the given sum. So now based on this Fourier transform condition, f of e power minus a t minus of 2. So this much 2 is shifting. Instead of T0 we represent by the minus of 2. So that means how much duration is going to shift in the minus direction. So that much will be going to multiplied in the Fourier transform of spectrum domain. That is e power minus a 2 omega. Here is 2 is there. That's why we replace for the T0 into 2. E power minus j 2 omega. What the remaining term? That is 2 by a square plus omega square, because of a is there here. So 2a square plus omega square. It can be also write as e power of minus a mod of t minus 2 Fourier transform is represented as e power of minus j 2 omega 2a divided by a square plus omega square. So suppose the given for the time shifting property to find for the Fourier transform of x of t is equal to e power of minus a t plus 2 mod. If they give what the answer for here, so that is represented as a Fourier transform e power of, here is plus 2 is there. That's why I should write as a j 2 omega into 2a divided by a square plus omega square. I write. Okay. If plus is there, then here is plus. If minus is there here, t minus of 2, then I should write as a here is minus. Here is minus. That's why I write as a minus 2 here. Okay. This is the time shifting property of Fourier transform in the numerical example. Next property is represented as a time differentiation property of Fourier transform. The time differentiation property of Fourier transform states that the differentiation of a function in time domain is equal to the multiplication of its Fourier transform by a factor of j omega in the frequency domain. That means if you are going to differentiate with the input side in the t, the output side is getting to multiply with the frequency factor of j omega in the Fourier transform condition. That is called for the time differentiation property of Fourier transform. Now, we should take for the Fourier transform of x of t is represented as x of omega. X of t is represented as x of omega. Then inverse Fourier transform take x of t we got. Now, what is it doing for this property? Time differentiation property. It's doing for the differentiate with the time in the input side. I write here. Differentiate with the input side. Differentiate with the time in the input side. D by dt x of t. The Fourier transform is represented as its produced output is j omega x of omega we got. J omega x of omega we got. Next, here in this condition, I should take for the inverse Fourier transform. So this is a Fourier transform. We write x of, that is Fourier transform of x of t. We write for the x of omega. That formula here I represent, that is minus into plus into x of t e power of minus j omega t dt we wrote. At the same time, if you take for the Fourier transform minus of this x of omega, capital letter x of omega, then this integration is going to change for 1 by 2 pi minus into plus into now the input, that is x of omega e power of plus j omega t d of omega. So here I write for the inverse Fourier transform. Here simply I write for the general term is x of t. Both the side is going to have the error mark. Fourier transform is represented as x of omega. If we take inverse Fourier transform of x of omega for here, then we got for the x of t. Now this is equal to x of t. X of t is equal to inverse Fourier transform of x of omega. That value, that formula is equal to 1 by 2 pi integration of minus plus into x of omega e power plus j omega d of omega. Now, taking the term difference on both sides, because of here we done for the time difference. So the time differentiation is going to happen for the only input in the x of t. That's why this term I do for the differentiation d by dt x of t is equal to d by dt 1 by 2 by integration of minus into plus into x of omega e power plus j omega d of omega. Now this differentiation I should put for the inside where the t is present. So here the right side of the equation 1 by 2 pi integration of minus into plus into x of omega. There is no t is there. That's why I take it out. Then d by dt e power of j omega t. Omega side have the t. That's why we take for the differentiation into d of omega. Now, if we differentiate for the d by dt of e power j omega t is equal to j omega into e power of j omega t. Okay, j omega into j e power j omega t. So if we differentiate for this value of e power j omega t in the time domain, we get for the j omega multiplication of e power j omega t. So you should substitute for it here. So that is 1 by 2 pi integration of minus into plus into x of omega j omega e power j omega d of omega. Now this omega we take it out. Okay, so I take it out for the omega. Remaining things, what is that? 1 by 2 pi integration of minus into x of omega e power j omega t dt. So this whole term is represented as a inverse Fourier transform of x of omega equal to x of t we got. So I should write for the j omega inverse Fourier transform of x of omega. So this inverse Fourier transform of x of omega we got. Now I should take for this term, entire term as a Fourier transform. That is Fourier transform of d by dt x of t equal to, this is inverse Fourier transform and Fourier transform getting to cancel. So that's why x of omega we get into multiplication of j omega. I should write here for the condition of Fourier transform of differentiation. So the right side, that is represents here, right side as well as left side, I should write Fourier transform of d by dt of x of t is equal to, here the Fourier transform of j omega f inverse of, that is f Fourier transform inverse of x of omega. So now this Fourier transform of j omega, we put it for the inside, for the in the inside bracket. Fourier transform of j omega is represented as a j omega only. There is no changes in the time or frequency, something is not there. Then Fourier transform inverse x of omega. These two are getting to cancel because of inverse. So finally what we got? J omega x of omega we got. So the Fourier transform of d by dt x of t is equal to j omega x of omega we got. This is represented as a time difference property of Fourier transform. So I represent for the d by dt x of t, both the side of arrow mark of Fourier transform is represented as j omega x of omega. In general, so this is one time we done for the differentiation. If we done for the nth order of differentiation, what it will be going to happen? So d by dt of, that is d by d power n divided by dt of n x of t is equal to, the Fourier transform equal to j omega n x of omega. That means if you differentiate with n time, only this portion only is getting to change in the Fourier transform. Then remaining we got for the same spectrum. Okay. So this is represented as a time differential property of Fourier transform in nth order differential cases. For here I take for the some numerical exam. The frequency derivative property of Fourier transform. Find the Fourier transform of t e power minus 2t u of t. So now the x1 of t I should take for the e power minus 2t u of t I taken. For this portion only I take for the x1 of t. Because of I need to prove for the differentiation property in the Fourier transform condition. Already we studied for the differentiation of Fourier transform of single side exponential signal function. This is we studied and you are going to start for the Fourier transform. Single side exponential function, the Fourier transform of e power at u of t is represented as 1 by a plus of j omega. This is we derived for last session. From the function x1 of t, what is that? We got e power 2t u of t is there. So that's why I write as a x1 of omega is equal to Fourier transform of e power 2t u of t. I wrote this where the a is there, that will be present for the 2. This is a equal to 2, you write. You substitute for this equation. So that is equal to 1 by 2 plus of j omega. Okay. So the x1 of case, x1 of capital letter x1 of omega is represented as a Fourier transform of e power minus 2t u of t. Instead of a, we use for the 2. The sum is given for the 2. Then where the a is present, the a is equal to 2, you substitute from this equation. So what is that? 1 by 2 plus of j omega we got. By using the frequency derivation x of t, the Fourier transform is equal to my j d by d omega x of omega. That is we represent as a frequency derivative property. So this frequency derivative property, Fourier transform of e power minus 2t u of t is represented as a j d by d omega f of e power minus 2t dt dt. If we do for the differentiation with frequency, what we are getting? The right side j is represented d by d omega, 1 by 2 plus of j omega is equal to j. If differentiate for this term, minus 1 j 2 plus of j omega whole square we got. Therefore, the Fourier transform is given the function f of t e power 2t u of t is equal to 1 by 2 plus of j omega whole square. Remaining portion all is getting to cancel. It can be write as t e power minus 2 u of t, the Fourier transform is equal to 1 by 2 plus j omega whole square. This is represented as a numerical example of differentiation condition in the Fourier sequence. Next, time integration property of Fourier transform. The time integration property of Fourier transform states that integration of the function x of t in time domain is equal to the division of its Fourier transform by factor of j omega in the frequency domain. That means if we do for the integration in the time domain, the frequency domain is going to divided for the j omega. This is called for the time integration property of Fourier transform. As per the statement of Fourier transform, we take for the Fourier transform of x of t is equal to x of omega. Then it's represented as a minus into plus into x of t e power of minus j omega t dt we write. So this term, this entire term I should write for like this term. X of t Fourier transform is equal to x of omega. So as per the integration property of Fourier transform, I should take for the integration of minus infinity to plus t x of tau. The Fourier transform is equal to x, capital letter x omega divided by j omega. If capital letter x0 equal to 0, this is a condition for the integration property. When integration of x0, capital letter x0, the value is represented as 0. Okay. Here also we taken for the inverse Fourier transform. That means what is that inverse Fourier transform? Inverse Fourier transform of x of omega is equal to x of t. You know, this is inverse Fourier transform formula. Already we discussed for the last property. That is x of t is equal to 1 by 2 pi integration of minus plus t x of omega e power plus j omega t dt. Sorry, d of omega. Now we should substitute or replace t into tau from the inverse Fourier transform condition. So I should write as x of tau is equal to 1 by 2 pi integration of minus into plus into x of omega e power j omega t d of omega. Next time, taking the integration on both sides with over the minus infinity to plus t. So I write for the minus infinity plus t for the right side. The integration x of tau d of tau is equal to integration of minus infinity to t 1 by 2 pi integration of minus infinity plus infinity in the right side x of omega e power j omega tau d of omega. Both side, left side as well as the right side, we do for the integration with limit of minus infinity plus infinity, that is the limit of minus infinity to 2 plus t and with d tau condition. Okay, now the right side we need to do for the interchange the order of integration. So 1 by 2 pi I take it out, integration of minus infinity plus infinity x of omega I take it out. Remaining portion what is that? The integration of minus infinity to t e power j omega tau d tau into d of omega is there. So if we do for the integration for this term, we got e power j omega tau divided by j omega. Okay, so the integration of minus infinity to t e power of j omega tau d tau. The integration with substitute the limit of minus infinity to plus t, then we got for e power of j omega tau divided by j of omega. After finally is represented as here, this is minus infinity to t. We got the output values represented as here 1 by 2 pi integration of minus infinity plus into x divided by omega j omega e power j omega t d of omega. This term is called for Fourier inverse of x of omega divided by j omega. So what we the case we write for the inverse case, how you got for the j omega in the condition of Fourier transform. We know the inverse Fourier transform x of t is equal to 1 by 2 pi integration of minus infinity plus infinity x of omega e power of plus j omega t d of omega we write. So this is we represent as a f inverse of, that is Fourier transform inverse of x of omega, that is equal to x of t. Now the condition that see for here where the omega, that is x divided by omega is there, that is j omega, x divided by j omega. That's why we write as this term is represented as a Fourier transform inverse of x omega divided by j omega we write. So that due to that condition I should write by like this term. Now we take for the Fourier transform for both the side. Okay, what we represent for in this case of integration left side as well as right side, what we got in the equation as Fourier transform of integration of minus infinity to plus t x of tau d tau equal to Fourier transform of x of Fourier transform of this term, that is equal to this term is represented as a Fourier inverse transform of x of omega divided by j omega. So now what will be happen? This Fourier transform, inverse Fourier transform get into cancel. So finally what I write, the Fourier this value is equal to x of omega divided by j omega we write. Okay, that means this term Fourier transform of integration of minus infinity plus infinity x after d tau is equal to x divided x capital letter x omega divided by j omega. That means if you take for the integration with the Fourier transform, we should get as a spectrum is divided by j omega. In general term, we write as a integration of minus infinity plus t x of tau d tau is equal to x of omega divided by j omega. This is called for the time integral property of Fourier transform. Next condition, we go for the autocorrelation property of Fourier transform. What is it? The case, the autocorrelation of Fourier transform in the continuous time function x of t is defined as r of tau is equal to integration of minus infinity plus infinity x of t x star of t minus of tau d tau. This term we call as a convolution case. So now we go for the statement of autocorrelation property of Fourier transform. The autocorrelation property of Fourier transform state that the Fourier transform of the autocorrelation of the signal in time domain is equal to the square of the modulation of in the frequency domain. As the statement in the Fourier transform condition, x of t take for the Fourier transform we got for the x of omega. By the autocorrelation property of Fourier transform, or tau of Fourier transform equal to mod of x of omega whole square. So now we need to prove for the autocorrelation function of Fourier transform. Now we take for the autocorrelation function. We know we got for the autocorrelation function is represented as a convolution sum with continuous time signal in the case of complex value. Now r of tau is equal to integration of minus into plus into x of t x star of t minus of tau d tau. From the definition of Fourier transform, we do for the x of omega, that is represented as x of omega is equal to Fourier transform of r of tau. I write. So now x of omega equal to Fourier transform of r of tau is equal to, we do for the integration of minus into plus into, this is Fourier transform, we know the Fourier transform of x of t is equal to, what do you write, that is integration of minus into plus into x of t e power of minus j omega t dt. This formula we should adopt it for here. So instead of x, we do to use for the r of tau. R of tau now we know that is equal to complex conjugate convolution of integration in the time condition. Now I write for the integration of minus into plus into. Next, the x r of tau is equal to integration of minus into plus into x of t x r of t minus of tau dt into e power j omega t dt. Now in this right side, by interchanging the order of integration, so this case where the star is, that is complex case is there, you take it out. Then in the right side of the equation is come for integration of minus into plus into x of t integration of minus into plus into x star of t minus of tau e power j omega t d tau dt. Now I should substitute for the t minus of tau is equal to u in the second integral. At the same time, tau is equal to t minus of u and d tau is equal to du. This all term we should substitute for this equation. Then the right side of equation, integration of minus into plus into x of t integration of minus into plus into x r of u e power minus j omega t minus of u du dt. Now this term I should split e power of minus j omega t into e power of plus j omega u. This two, instead of this term I should substitute here. I got like this term. Okay. So after that, substituting that value, we can split for both u is one side and t is one side. Then integration of minus into plus into x of t e power j omega t dt. Integration of minus into plus into x star of u e power j omega u d of u. This is purely u term. This is also purely u term. So I take it out for this complex conjugate of this x of u in the entire term. Then automatically e power j omega u is changed for the minus e power j omega. Then this term I write as a x of omega and this term I should write as a x star of omega as per the Fourier equation. So that means x of t of Fourier transform is equal to x of omega. So this x of omega equal to integration of minus into plus into x of t e power of minus j omega t dt we write. So instead of this term I write as x of omega, or instead of this term, because of this is going to have for the star. So that's why I put for here is star. This term I write as a x star of omega. This is complex conjugate value. So now this term we represent as a x star of omega. Now Fourier transform of r of tau is equal to x of omega x star of omega. This term I should write for the mod of x of omega whole square. It can be represented as a, that is autocorrelation function of Fourier transform r of tau is equal to that is x of omega whole square, mod of x of omega whole square. So up to this much I am going to completed this section. I refer for those property from the signals and system communication B Hatti and AB Openum. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.